Hi, Fran.
Hi, how are you?
Um, for the project, can we just send it to you through Slack, the GitHub link?
Uh, uh, GitHub link, right? That should work, yeah.
Uh, Hear you. Can you say it one more time, please?
Yeah, I'm saying GitHub link is fine. If you can share the GitHub link, I'll just pull the code and run it on my side.
Okay.
Yeah. So I think just only about 30 minutes of content for today. So let's wait for another minute or so. Yeah. So okay. I'm sharing the notebook for today, which is basically the same notebook that we were using on Friday, but it has a few changes that I made. So going to share that in the chat. So we just want to wrap up what we did on Friday, and then there is a very brief walkthrough and a summary of everything that we did this week. And then at the end of the summary, there is a few readings that will make sense now.
Uh, just Farhan, I had one question regarding this kind of like assignment or homework. So we need to submit by Saturday or Monday. Uh,
So 7th is what I had communicated to Marisa, but if you
oh,
are
okay,
having
okay,
difficulties, then let me know. We can stretch a little bit.
okay, sure. Thank you.
Sure. So if we have the notebook, then just probably go ahead and run it because it's mostly the code is mostly what we saw on Friday. Yep. So we are actually totally done with the code for the environment itself. It was working. We saw that the agents were also moving around, and then we were thinking if we could solve it with the same techniques that we have used earlier. Most of the functions are uh, going to remain the same, but if we want to print the policy, then it's going to be quite a bit challenging because number one, we don't have access to the entire state, and then there are such a huge number of states, 300 or so. How do you print them? Right. So I have modified the pretty print policy function quite a bit. uh, it is still very challenging to visualize the entire policy as a whole, but what I have tried to do is look at individual configurations. So instead of trying to look at the entire policy, like that tells you how to proceed at every step, we can just try looking at the immediate action for every configuration. So that is what I have tried over here. It isn't still perfect. and I'll show you with an example. But the rest of the code is pretty much the same that we were using earlier. Only the number of state has been sort of hard coded to 320. So I'm running this code that we derived using constant alpha before we started TD learning basically. And it takes a while to.
Why it's 320? Is there any special?
Yeah, so the way we are encoding things, if you look over here, so the number of observations that is going to get multiplied by 16, right? And so we are basically combining the state of the player and then the state of the opponents, right? And the player will it could be in any of the 20 states, and for each of those 20 states there are roughly or the maximum number of possible opponent configurations is 16, because each of the opponent, north, south, east or west, could be present or absent. So for each of the 20 states in which the player can be, you have 16 configurations. That gives you 320 states. Of course, not all of those states will actually occur, because when the player is, for example, near the edge or near the boundary or near the corner, then of course many of those states will never happen, because the opponents can just not be present north or west of those positions. We will see that when you look at the table, there are many states that just remain empty even if the training process is over.
See, thank
But
you.
it basically boils down to the encoding we are using. Is this like, are you able to understand why we have 320 states? So observation basically is a tuple. The first part is the state of the player, this one, and this one is the configuration of the uh, opponents, presence or absence of the opponents in the four adjacent cells, right? So this is a dictionary which has four keys: north, east, south, and west, and then corresponding to every key, you either have an opponent, which means it will be one, or you don't have an opponent, in which case it will be zero. And then we are taking this observation, we're multiplying it by 16, and then we are adding, encoding the rest of the configuration and then appending that. This number will be between 0 and 319. So looks like we are done with the episode based training, where we were using entire episodes. We ran for 5,000 episodes, and this is the table. Of course you can't see all of it, it's very tall, 320 rows, but even then you can see lots of rows are empty here. And this alone does not tell you if this is a good policy or not, if all the states are properly being updated or not. But and we can try, there is a little bit of code over here that we can just quickly try to see if this policy is at all giving us good results or not. I'm not expecting it to be, because this has just trained for 500 episodes. So uh, yep, what was the table called? Estimated returns. Yep. I'll actually comment out this line. Just want to see how many steps it typically takes. I'm trying to play, sorry, need to comment out this one as well. You just want this print statement to tell me how many steps it generally takes. Right. So with 5,000 steps, a typical game is taking like 150 steps and or 200 steps. And you can try printing the actions and you'll see that it gets stuck a lot of times. Okay, we can again try to improve things, maybe train for more episodes, tweak the other parameters. But since we know that TD generally converges faster, so we'll bet on both SARSA and Q learning. Okay, this is again the standard implementation of SARSA that we did the very first time. I have again added this visits table. This was purely for debugging because I wanted to see if any of the states were being left out for any reason, because there were a lot of zeros in the Q table. But it turned out well. So there aren't any changes to the logic except over here, where now we are encoding the state. So this is the raw state that you get from the step function, and then you need to encode it using the function we wrote that I was just showing you, which will map it between 0 and 319. Right. So everywhere you are using a state to index into the table, here, be it here, here, or here, uh, or over here, we have to use the encode function. Okay. Steps is set to 30,000. And this will take, although it's showing us 30 minutes, it's going to speed up very quickly. So it will probably take 5 minutes. And we just want to quickly see if this is working or not, because now we have made the environment dynamic, the players can move around. So is our algorithm able to detect all of those patterns or not? I'm sorry, I just noticed the chat box. It will take a good 5 minutes to train. Uh, and we aren't training for too many episodes. It is just 30,000.
Did you say to 30,000 because it wasn't converging?
I was actually, I started with like 50,000. I was trying different combinations of the parameters. And with this value of min epsilon and epsilon decay and alpha, I was able to get, when I looked at the graph, I was able to see that around 30,000 it pretty much converges. After that, it sort of flatlines. The problem is that now it has become a lot more difficult to visualize things. So the pretty print policy function isn't very helpful right now. We will go back and think about what can be changed. Right now it is just dumping all the 320 states in a visual form, which isn't very helpful to understand. And at this point, with something of this complexity, we also have to start thinking about the training speed. So, profile being able to just profile the code and see where time is being spent, and then trying to just using different techniques, shortcuts, tricks, whatever, to reduce that time.
For the encode and decode debug that we saw last time, what was the issue?
Uh, there was no issue. When I was kind of demoing my code, there was a bug when I was trying to run the encode and decode functions. I wasn't passing the right type of parameter. But what you see over here, this is perfectly fine. This will work.
Yeah, wasn't the encode having the issue before? Because it looks the same as what we had last time.
Yeah. So these definitions were all right. There was no issue with the definitions. There was another cell over here where I was just trying to test them,
Oh
and
yeah,
while
yeah,
testing, I was passing the wrong type.
I see.
I think I was passing the entire return value instead of just
Mhm.
the observation part. Okay. Sorry. So we are done, and you can try printing the policy. It will output a lot of things, but I just want to quickly show what it tries to print. Right. So in the very beginning, it tells us that the state of the player or the ball is 0, and then this is the dictionary that is telling us how many defenders are present, and this is the Q table that is telling us that the best action to take in this scenario will be to go north, east, west, and south. The best action is to go south. This one is for staying put. Uh, and so it's not printing, even trying to print the entire field, because now we have incomplete information, so we don't know where the rest of the defenders are. So what I have tried to do is just print the ball in the center, and then also try to show any defenders that are there to the north, south, east, or west, and that would be over here. And then just print the immediate step that the policy tells us. So in this case, because all four routes are open, it's telling us south, which is sort of sensible. We don't know where what the rest of the field looks like. So only with this much limited information, this looks okay. And then in the next state, there is actually a defender right below, and the policy says we should go up, which again makes sense to me. Then over here, the policy is telling us to go north. Again, looks okay. There is nothing that suggests that this policy could be wrong. Right. Uh, Over here, we don't know why it says we should wait, but we don't know. We are not looking at the entire field, so there could be reason why the policy is telling us to hold in this cell. And so there's a lot of output, all 320 states. We can tweak the function to only print things corresponding to one of the states that we are interested in. But it's really difficult to be able to visualize the entire policy, because now there are so many moving parts, you just can't plot them in 3D space. Right. But what we can do instead is two things. One, we should plot the 100 episode reward, which looks like this. So it is certainly above zero. You can also try printing values. They are generally positive integers. I also tried printing the number of visits, which again nothing. It doesn't tell me anything conclusive, but this is something to use in debugging. If I suspect that a state action is not being visited at all, then I might be able to look that up here. But what I really did was just try to play the game a few times, see how many steps it takes. So in this case, it took 11 steps and it scored a reward of perfect 5. You can see how. So yeah, I started like this, then moved southward, then east, which seems safe, then south again. Now, in this situation, it just can't move. So I think it tried north. Yes, tried north, but at the same time, the player also moved out of the way. No, it didn't. So like the agent went north, and then it tried going east, which sort of makes sense at this point, because given the information that the agent has, it only knows about this cell. It can't see beyond this cell that two other defenders are present here. So it is trying to see if it can, dodge the defenders over here and just take a detour from this side. But again, it reaches this point and it sort of comes back, and in that process, I think, okay, it tries to go east and then actually bumps into a defender, then tries to go south. The defender also moves south, and a lot of things happen. But uh, so this isn't perfect gameplay. It is still bumping into the defender, but in just 11 steps, it is at least able to score the goal. And we can try a few more times. This time it took only 7 steps. I don't think it ran into a defender anywhere. It did, uh, but still. So the number of steps isn't very large. It's sort of able to score the goal. Now the issue is with bumping into the defenders, and I think we might have to tweak our reward a little bit to like make it learn that behavior. But this seems okay given that we have only trained for 30,000 steps, and it has learned to sometimes dodge the defenders, sometimes, because defenders are also sort of unpredictable. Uh, they will go up or down randomly. So it is naturally difficult for the algorithm to learn the pattern as well. And then there is Q learning, which is again, you can train for a similar number of episodes, and the results I got was pretty much similar with the same settings.
I have one question.
Yeah,
So in the testing that you're doing, the reward doesn't have any discount, right?
right.
But in the training, you are using the discounted reward or return for training,
Right,
right?
right.
Okay.
I think we discussed that because, like with, for example, regularization in deep learning, you only apply that when you are training, because you don't want your training to overfit. So you are applying discounting to training because you don't want your algorithm to to learn a behavior where it is just wandering around or where it takes too many steps to reach the goal. But once you are certain that the algorithm is trained, in the end, what we are really interested in is the actual reward that it's able to get. So discounting here doesn't make sense. We need to look at what is the highest score that the algorithm is able to get. Yep, that's pretty much it. Now the things that we need to think about is, if you look at the table, a lot of these cells are empty. Some of them could be empty because there's no way that that state will occur because they are just impossible. For example, I talked about states where the player is suppose in a corner cell, then corresponding to that there will be configurations where we are assuming the presence or absence of defenders to its north or to its west. For example, at the top left cell, that those states will never occur, so it's fine for them to stay all zeros. But then there would be states which didn't occur because we never happened to pass through those states, because we once we started uh, relying on the table and being less and less random, then the chances are that there are states which are feasible, but we never visited them, so they are all still zero. And if we happen to run into one of those states during evaluation, then of course they will cause problems, right? So one thing that comes to mind is that if you think about how states differ, right? So every state is a combination of the player's position and the configuration of the opponents. Now we know that given the same configuration of the opponents, no matter, I won't say no matter, but in most of the cases, if the configuration of the opponents is same, then the actions you take will be similar, because you only know about that part of the field. We are not even passing where the goal is or where other opponents are. Then the agent should typically take similar actions, right? So even so, is there a way to do that? Even if we have never visited a state and we know that, and suppose we encounter that state, then can we get that information from a similar looking state, right? And this is all the more applicable to continuous problems where your action space and your basically state space, either of them or both of them are continuous. Then you it will never happen that you will be able to generate all combinations of all those possible variables. You discretize them, and then the assumption is that if two different continuous variables, when you discretize them, if they fall in the same bin or in the same cell, then they should generate similar actions. This is something that we will actually tackle in course 2, but the idea sort of has its roots here, that in this table we are still doing discrete learning, but there are lots of states which are not mapped to actions, and these states could be similar to other states. So number one, when we are encoding things, then we have to see uh, how can we ensure that nearby states have, when you encode them, they also in the target domain, which is between 0 and 319, they are nearby. And then the second part is, if they are nearby, then how can we ensure that we can sort of guess the policy for them, even if we haven't really uh, visited those state action pairs. So that is something to think about. And then of course being able to debug this policy is is another issue, because right now uh, it's not very helpful. And again, the same idea is helpful. So when you're trying to debug, I think it makes a lot more sense if we can just bunch together all the, for example, look at this configuration, right? So this is only telling you that this is when you have the ball in the center, and then you're surrounded by opponents in your north, west, and east. right? Now this ball could actually be anywhere on the field, pretty much anywhere on the field, right? So I think what would make more sense is that instead of, for example, in this case, the ball is in state 19, which is the goal state, right? But even if the ball was in state 15, this configuration is probably even possible there, right? And the action most of the time would be to just evade these opponents by going south. So it will make sense to combine or at least print those configurations next to each other. So I can just eyeball them, you know, in one glance, because right now they are scattered all over, right? So this kind of configuration, this will be repeating. It would be present somewhere else as well, but it would be far away from where this configuration is getting printed. So the print logic should be such that we know that the configuration of the opponents that sort of groups the actions as well. So if it is a similar looking configuration, then the action should be something similar. So that is one thing that we can change in our pretty print function as well.
But
And
right
then
now
same,
for all the Q table, everything's showing zero, so that's why it's showing the up arrow, right? Because it's the first
yeah.
one.
So yeah, right. So these are also, because right now we are printing everything, all possible 320 states, many of which are just not reachable. So they are all zeros, and yes, that is why you are seeing an upward arrow. So
But
it
this
really,
diagram isn't helpful, right? Because there's
sorry.
no information in the Q value.
Right. So in cases where the where these are all zeros, this just doesn't add any value. We can just exclude them as well. Right. So wherever the state is all the Q table is all zeros, that row, then there is no policy defined, and it's just going to pick up the first action. So we can just exclude them to be able to look at states where we actually learned something.
Okay. And I guess the pretty print policy is just going through all the different observation state and just printing it out.
Right.
Okay.
Right. And the second thing, of course, what I talked about is just bunching together states where the opponent configuration is similar. Uh, that will help a little bit. And then, of course, if you want to get really good performance, then you will have to get down to individual instances and like record the gameplay and see what could be going wrong, because whatever learning had to happen, most of the learning happened over here, right? This graph actually seems to be, maybe, I don't know if it's an illusion or if it is actually going a little bit downwards, but most of the learning actually happened in the first 5,000 episodes or so. And that is also something that we want to figure out, if we actually want this thing to happen, or we want a more gradual learning which actually is able to learn farther. It doesn't flatline, so perhaps decreasing alpha a little bit, and we can try having different schedules for alpha. So maybe start with the higher value, then slow it down a little bit over time, and likewise for epsilon as well. So yep, so this was the solution. This isn't 100% perfect, but it is okay, getting sort of okay results. uh, the next step, really, if you want to experiment, would be to just expand the field, or even before expanding the field, just allowing the players to be able to move in all directions. And then after that, just introducing a little bit of AI intelligence in these opponents. So maybe they are tracking the ball, maybe just they are trying to block the line of sight between the ball and the goal, whatever type of intelligence you want to add, and then see if the agent is able to run or not. And then after that, try to expand the field, more cells, more players, but the approach remains the same. But when you're dealing with a more complex problem, then obviously you will have to think about, it makes more sense to first debug this situation and understand it really well, and then scale up and aim for a bigger problem. Okay. Any questions, any doubts at this point?
One question I have is you were mentioning regularization is to prevent overfitting, right?
Yeah, in the
Earlier.
case of deep learning.
Um, and so in reinforcement learning, we don't have any regularization, anything, right?
Uh, we will have regularization if we were using, instead of using the Q table, if we were using a neural network, then regularization might come in.
Okay.
Like you might want to use dropout as a form of regularization. Cool. Okay. Okay. I just want to summarize everything that we did this week. So in terms of the syllabus, we have everything covered except for discretization, which is dividing a continuous space into discrete space. So we can again use the same table and same approaches. I am going to talk about that. But first up is a summary. So we started by introducing uncertainty through bad actions. This is what we implemented in our first session in week 4, right? So we introduced the concept of bad actions, and with a small probability, it was possible for the environment to take an action which wasn't the same as the desired action, the action that we sort of wanted the agent to take. Right. And then we tried to see if the algorithm is able to learn that behavior, that probabilistic behavior, and it seemed to do pretty well when when you apply this concept of bad actions. Then of course the outcome at every point is a distribution. So whenever the environment is going to step, then there's a range of possibilities instead of there being a single outcome or a single goal next state. There are many different states possible. When the environment actually takes that step, then obviously it will only pick one of those states, but it is free to choose from a bunch of states, right? And the aim was to see whether the algorithm can learn that behavior or not. That it's also possible to get this outcome when the current state was this, and then we took this action. And with little modifications to SARSA and Q learning, both were able to learn this behavior. They were able to uh, train pretty quickly, and and we didn't make any changes to the logic or uh, anything of that sort at all. And that was happening because ultimately all these, be it the last method that we tried, which was based on the Monte Carlo method, which was based on sampling entire episodes, or be it the TD learning approach, in both the cases we are learning everything based on sampling, right? So if it is so that there is uncertainty and there are different outcomes possible, then if we get enough samples, we will also be able to learn this behavior. And that indeed seems to be case when we tried both both Monte Carlo, SARSA, as well as Q learning. All of them were able to converge pretty fast. I think within 5,000, 10,000 steps, they were able to converge and learn this behavior. Of course, it will depend on how much uncertainty we are injecting. If we make the environment just random, where there's an equal probability of going into any of the next states, then it should be pretty hard to learn that for any algorithm. But we kept that probability low, zero point 0.1 or so, and in that case there wasn't a lot of added burden on the algorithm. It was able to learn quickly. The next thing we did, which was on Friday, was making the environment dynamic, allowing the players to move. Right now that is random movement, which I think is even harder to anticipate and learn. But what we saw today, that seems to indicate that it is indeed possible to learn that behavior as well. And like in just about 30,000 steps, we were doing okay on what seemed like a complex environment. It is complex because if you look at the observations, number one, it's a very limited field of view. You're not able to look at the entire field. Things have changed a lot. Earlier the field setup was totally static. Now everything is dynamic. um, and But we are only allowing you to see so far just a radius of one cell, and the algorithm is still able to detect those patterns, it's able to learn them. And also the way we encoded those things, so the algorithm should be able to understand, sort of decode how information is encoded and what makes up the states. So that was possible with just 30,000 steps. Yep. So what we for the first the thing we introduced for the first time was this concept of incomplete state observation, where we were just allowing we were being more realistic and just allowing four neighboring positions to be seen or sensed, and this is sort of going to be the case for most real world environments. So that was the case, and then we sort of left it to the, you know, the person who is developing the algorithm to encode the state efficiently, because there were multiple ways we could just have left the, instead of encoding everything, we could just have placed bit vectors next to each other, the bit vector representing the state of the player and the bit vector representing the presence or absence of opponents, and then encoded the whole thing. And that would probably require a lot more number of states, and it would certainly be a lot more difficult to learn that mapping, because then obviously you need a proportionally high number of episodes. So we settled for something where it was most compact sort of state encoding, and this is going to be a big problem when we are going to deal with uh, more high dimensional data. For example, if we just start looking at the image frames, right, the frame buffer that you render. So it could be the screen capture of a video game, or if it's like it's a robot, so it could be the stream coming from the video stream that is sampled every few frames. So if you are going to look at that kind of high dimensional data, then the first thing we need to be we need to start thinking about is how to encode that efficiently, and that would be possible with neural networks. We'll see that in course 2, but we sort of saw a glimpse of that here, that it is sort of up to us, the developer of the algorithm, to decide which encoding to use, which format to use, so the state space doesn't blow up, and then it's easier for the algorithm to learn something meaningful. All right. There are a few things which we didn't cover, but should be very easy to understand with what we know now. One is this concept of TD lambda. So we went from Monte Carlo, where we were sampling entire episodes, and then we just started looking at individual steps and updating at every individual step. But there is also a middle ground where you can simulate a few steps and then update the state and then simulate a few steps. So what we were doing was practically a special case of what is known as TD lambda, and we were using a lambda value of 0. So we were just using one step of the simulation, one step of the gameplay. There are two links included here. The concept is really straightforward. Like TD lambda itself is straightforward. Like I said, that you simulate for more than one step, but then there is an issue of reward assignment. Like there are many states, so how do you update those states? How much the Q value or the estimate table should update corresponding to each of those states, right? And that is covered in the first link. And the second thing that we didn't really cover in terms of writing code for things is discretization, right? There are three different links, because there are sort of three different approaches that have been used to discretize space. The idea is very simple. If I want to discretize a range, I'll just break up the range into different sub ranges, and then I will, be it my state or action. So if, for example, if we were talking about the steering angle, that goes between -25 and 25, so I can break that range into 50 different bins or 100 different bins. That will depend on uh, a few factors like how much how complex and how sophisticated my algorithm has to be, and how much time it should take to train. But that is like the basic idea is same. But then the other problem we were talking about, which is nearby states having similar actions, right? So it shouldn't happen that if the continuous value of the steering just changes by zero point 0.1 degree, uh, there is a big difference in the output, right? So to fix that, there are, instead of using just one set of bins, people usually take multiple bins and overlap them, so any position is covered by multiple bins. And then based on that membership, based on that membership, you can sort of encode each of the any continuous value. You can encode that as a discrete value, because you will just be able to find which bins that continuous value falls in. So that is one approach. Then that is more of a binary approach. So you will see, if I have a steering value of 5.2, then 5.2 will fall in different bins, and I will encode that. And the membership is basically binary, so 5.2 either belongs to a bin or it doesn't. And then there's a function based approach where you imagine that every bin has like a normal curve or Gaussian curve sitting in its center, right? And any value is you basically measure the probability of that value belonging to that Gaussian, and that becomes a value between 0 and 1. So instead of using just binaries, your features or your states are composed of numbers that are between 0 and 1. And then there is third approach as well, which is very similar to creating bins, but this is more like random bins than uh, very structured and regular bins. So those concepts are covered over here. We aren't really going to use them, because when we start with course 2, we are going to be looking at much more high dimensional data, so we'll probably directly start with the neural networks. But one thing that would make a lot of sense would be to combine the techniques that we have used here. And we have already made a lot of changes. We just started encoding state ourselves, and just go one step ahead and add one of these discretization methods. So take the problem that we handled at the beginning, which was driving a car across a track, and sorry, and discretize its state space, which was basically its position, the coordinates, and its velocity, and its action space, which was its steering angle, and uh, its I think steering was the only variable that we were changing, right? So discretize them, and then build a similar table and use the same similar technique, and see if we are able to learn that behavior which we did using PID. But that will be interesting in itself, and that will directly lead to what we will do in course 2, where we will use neural networks but for a similar purpose. So to be able to deal with a larger state and action state space, and also be able to deal with continuity. Yep. So in terms of the only remaining bit is there, we went over the entire terminology last week. There was one bit remaining, which was the equations, which are, yep, we went over everything except these Billman equations, right, which you will generally find in the textbooks. So they will take different forms depending on whether you are dealing with an environment which has both it will depend, the form will depend on the type of the environment, so whether it's stochastic or regular, and then also on the policy being used. Normally when we are training, for example, we are using a stochastic policy as well, right? Epsilon greedy policy is stochastic. But if your policy happens to be a fixed one, so it will look a little different. But what you see over here is just the most general form of the equations, right? And it's not very different from what we have written in terms of code, but I sort of want to go through what they say, try to explain. So the Billman equation is basically the recursive equations that we have been using all along with dynamic programming, with TD, with Monte Carlo, everything, right? So over here we are trying to define the Q value, which is the returns for a state is 0 and A0, and the subscript pi is saying that at this moment we have some policy pi that we are using to determine this value, right? Obviously, the first thing is the immediate return, which we know from the state and action. So this is the immediate reward. So this is the immediate reward. Then you have the discount factor, but then there is this slightly confusing last term that I want to explain. So what is going on over here is that now we know that our environment is likely stochastic. So when you take action A0 and A0, there are many different states possible. So there could be several S1s over here, right? And each of those S1s, for each of those S1s, we will have, uh, we want to find the, what is called the state value, which we are representing with V, which is basically if you remove the actions, then the best return you can get is the action value, right? The state value. So this is nothing but multiplying by the probabilities, right? Suppose there are 4 different or 20 different states possible corresponding to S1. So each of them will have, or most of them will have a small probability, and whatever that probability is, that gets multiplied with uh, their return, the return you can get from that state S1, and then you sum that up. So this is actually a weighted sum or an expected return value instead of a single return value, which we were using earlier, right? And then this part itself is probabilistic. So if you think about what the state value of S1 is going to be, again, because in S1 there are in our case there are 4 possibilities, right? So uh, this is like this taking the second step of your Q learning. So there are 4 different, or how many ever different actions possible, and again each action has a probability. This time the probability comes from the policy that we are using, right? So this probability over here, this was built into the environment, right? So if the environment was stochastic, there must be this probability table hidden somewhere, or some rules somewhere that decide the probability of each of these transitions. But this probability comes from the greedy policy. So this is just taking the probability of action A1 while you are in state A1, and then multiplying that by the Q value corresponding to this state, right? And we can just substitute this entire thing over here, which only makes this equation even more complex. But if you substitute it over here, then you will see that this is nothing but relationship between the Q value at S0 A0 in terms of the Q value for S1 and A1. The only thing we have done is that we have defined this intermediate variable V of S. We saw this notation when we are trying to implement Q learning and SARSA using uh, this book, I think, right? So we saw the concept of V values, and right. So they were using V values. We weren't mentioning V values because we were directly defining Q of S0 A0 in terms of Q of S1 and A1. But it helps if you define this intermediate variable. So this is what is known as the Billman expectation equation. There is also a Billman another pair of equations where you use the maximum operator. If you just want to learn the optimal policy, then of course you're not interested in the the expected value of things. You are interested in the maximum value. So that is again described in the book. But the general idea is that we have been using Bellman equations all along. We didn't give them any names. And of course, you can't really use Bellman equations in this form because the P over here, this is unknown. So we were trying to estimate things using a similar approach. We weren't exactly using these equations, but these are like if you really want to derive things from the basics. So this sort of makes sense, because if there are many possibilities, then of course if I talk about the expectation value, any sort of action value or expectation value, then that should be uh, an average of everything that is possible. And that is why they introduce this probabilistic sum over here and this one over here. Uh, Other than yeah, I think this was the only bit of terminology that we didn't talk about earlier. We didn't call them Bellman equations, but we were using them in our code. So I think with this we are done with our syllabus. Like I said, discretization is important. Do try to implement one of the simplest discretization methods, which is I think tile coding, which is number 2. So try to implement that for the car environment. Should be really easy, and then it should be actually fun to see if this works. If you just introduce discretization, and then if you're able to train the car to drive on the track. And yep, some of you have asked about course 2. So for course 2, we will have to wait for a little while, because we have the deadline for submissions till 7th. So I will have to wait for that, and after that, Marissa will let us know if we want to have course 2 right away, or we want to have another batch of students who want to go through the first course that we did, and then we'll do course 2 sometime later. But please make sure that you send your submissions, and it's just okay if I think the easiest thing is to just commit your code to GitHub and just send me the link on Slack, DM me the link, and I will evaluate everything before 7th, and then I'll let you know if there are any issues with the submission. And based on that, I'll be able to share the list of participants who are able to sort of finish the course, because if you submitted the project, then that means you're done with the course.
So I had a few questions about the project. The final rubric, is that under the week 3 office hours, or is that somewhere else that you have the final rubric?
Yeah, no, it's under week 3 office hours.
Okay, cool. And for the documenting of the solution, that was the thing I think I was most confused about, because I optimized the hyperparameters offline on my local machine. So can we just kind of say, okay, we did some trial and error exploration and give the final values of the hyperparameters, or do you want some much more detailed?
No,
analysis?
I just want a very general approach, just a few lines telling what at least what different combinations you tried. That should be fine.
Okay, and do you want results for both SARSA and Q learning, or is it fine if we just submit one?
No, just one algorithm is fine.
Okay. And then the last thing was I wanted to try like this hierarchical learning from the Dietrich paper. The problem is that the API doesn't have things like the terminal states or pseudo rewards or things like that. So I was wondering if I could kind of hack the API and add things like giving a reward and a flag if I've reached the passenger or stuff like that.
Yes, absolutely. That is a good thing to try. And you can definitely very easily extend the environment. Just extend the current taxi environment and add whatever functions, whatever intermediate rewards you would like to add.
Okay. So in Python, if we have a class, let's say, for example, like the taxi env, how do we add a method to the class?
Pretty much the same way like in C++ or Java. You use the same class name. And by default, when you're creating an object, so by default, it will call the method which is in your the child class basically.
Oh, so you're saying like use inheritance or something like that? Yes, so have another class that inherits.
Yeah, so if you look at the taxi environment, that is already inheriting the discrete environment class. But you will probably also want to override a few functions, right? That is what we are interested in. So you can just redefine the same functions, and when you do so when you create an object, automatically that redefined version will be used.
Okay. Okay, cool. Thanks.
Okay, are there any other questions about the solution or the project?
Just an observation, Plan. In the taxi, or maybe in all the other games or all the other environments as well, there seems to be a maximum episode length set in the gym environment itself. Like if the episode length reaches 200, then the done flag is automatically made true somehow. Any reason why this is done, or do you have some insights on that?
I think it should be the same reason, that we set a maximum episode length, because there will be instances when things will get stuck and you want to start a new episode. I don't think this is
Okay.
theoretical. That.
Okay, but I think it's 200 for all of the environments, I guess.
Okay. I
Okay.
think I noticed that with the taxi environment, but I didn't know that this is present in all the environments and this is a single number.
Okay. Even I didn't check. I just thought it's the same because I didn't see anywhere it being defined in the discrete env or something.
Right.
So I think somewhere it's in the gym.
I'll check that. That is actually interesting. We should be aware of that. If you ever want your episode length to be more than 200, then
yeah,
they will be just assuming it is.
I was just trying out the random search. So
yeah. And the other
came
part,
up
I
with
think you mentioned that, right, where which seems undocumented. I don't know if it is totally undocumented or is it because they are using hierarchical learning, so they want to introduce something in the middle. Basically,
Yeah.
the taxi can do a drop off in one of those 4 marked cells, and there is no
Yes.
penalty for that, even if the location is
Yeah.
incorrect.
Yeah.
And that is also very interesting.
Yeah, actually, one thing that's unclear is the taxi in theory can do a drop off anywhere. So if the taxi drops off the passenger in a without being an RGB or Y, then that state is actually undefined, right? Because now the passenger can really only be in RGBY or in the taxi. So I'm not even sure what the state would be for what happens when the taxi does a drop off in a location that's not RGBY.
Yes, we will have to see what exactly it is. I didn't think about this. I did see that it is able to make a drop off anywhere and not get penalized, which was strange. But now you are right. We will have to see what exactly happens. Like if the state is undefined, then what happens next? I'll check that.
Yeah.
So you can feel free to set it less than 200, right, steps for the episode, right?
You can set less than 200, but if we set over 200, then we won't know, but it will actually automatically terminate by 200 steps. That is.
Yeah, I was actually treating that as another hyperparameter. What max episode length I wanted when I was doing the random episodes.
Right. Cool. Do let me know if there's anything. Ping me on Slack. I'll reply. Like I said, I think I have gotten 2-3 submissions so far, so I'll just evaluate them. But everything will be done by 7. So just make sure you turn in those submissions, because then based on that, by Saturday or so, I will send the list of final completions. Okay, I'm just wrapping up. Thank you all once again for signing up, and then actually coming to the class every day was very interesting. I hope we have course 2 soon. That will be even more interesting, but we'll have to see. And this Slack workspace is kind of forever, so if there's anything interesting you want to discuss, just let me know. And you also have my email address if you want to reach out to me.
So Farhan, so this kind of like submission needs to be done by Friday, right? That's all this.
Yeah, 7th
Okay.
is what I have communicated to Mariza.
Okay. 7th as per kind of 7th as per kind of is like the US timing or India timing.
Oh, that is fine. That shouldn't be an issue because anything I get by 7th India time, I'll probably it will take me some time to evaluate everything. So I think it won't be until Monday that I share the actual list. But just to be on the safer side, try to submit by Friday.
Okay, sure. Thank you.
So I actually just looked back at the taxi environment. It looks like what happens is when you drop off in a location that's not one of the 4 marked locations, the state just doesn't change. So you get a penalty in terms of the reward, but the passenger stays in the taxi. The drop off doesn't actually happen. So you say, I want to drop off, the passenger stays in the taxi and you just get a reward of -10. It's like trying to go off the board in soccer.
Yeah. That would make sense sort of, because then I was able to see the behavior where it sort of continues from there. But then the question is, why is this behavior introduced at all? Because there's no documentation in the code. In the paper 2, where they're describing the environment, there is no such description. But maybe the way they are organizing different subtasks.
Yeah, so what the paper does, if I understood correctly, is in the hierarchical learning, they don't even allow you to take actions like drop off if you're trying to complete a task of getting to the passenger or getting to the last location.
Right. They
because
have
they have a
defined a
terminal
navigate
state.
task.
Right. They have a terminal state telling you, not just, okay, did you get to the last location and drop off the passenger, but they have a terminal state of, did you get to the last location? And until you get to the last location, the only actions you can take are moving around.
Correct. That could be the reason.
But maybe I misunderstood.
No,
But
I think
that had been my understanding.
I just read the paper very superficially. I did not notice that there was a task about navigation, which didn't really bother about dropping off or picking up, and I thought that is why they are sort of allowing this.
So actually in the rubric, when you say that we have to have no illegal actions for that 1,000, what are the illegal actions? Is doing a drop off in a marked location illegal?
Yeah, illegal at that point we didn't know, but illegal basically means whenever you are actually getting penalized. So whenever the environment tells you it's a penalty of -1, which would mean that you are trying to drop off in an incorrect cell, not in the middle of the journey, but at the end of the journey you are dropping off in the wrong cell.
Okay, so we should basically be flagging as we go that we never get like a reward of -10. So no illegal pickup and no illegal drop off at a non-marked location, but a drop off at a marked location, even if it's the wrong location, is not illegal.
That is when it gets illegal, right? Because if it is unmarked, then you are free to try to drop off, and like I said, it doesn't really do a drop off, and then there's no penalty. But if you go to one of the marked cells and then you want to drop off there, and that gets you a penalty of -1. So basically, it's to be very precise, you don't want any penalties. So if you're not getting any -10s in your last 1,000 episodes, then that is the behavior you want.
But that -10 occurs if you drop off other location, not at the marked ones, actually.
My understanding is, I could be wrong, but my understanding is one of the marked cells is the correct drop-off location. So of course, if you drop there, you get +20. But if you drop off in, say, the correct location was G, and if you drop off at R, then there's a penalty of -10. I was just looking at the code.
No, there's only a penalty if you drop off at an unmarked location.
Okay.
Yeah, in the other case, it marks you, maybe you get off, right? And then, let me see.
Yeah, that's correct. It gets dropped off from there, and so you have to pick up again from there.
Yeah.
Like we were discussing, it doesn't even really drop off because the state doesn't change. So the passenger
it's not dropped off even. Yeah.
Okay.
So which are the illegal actions?
Yep. So illegal action is basically the else condition over here. Oh, sorry, I'm not sharing my screen. 1 second.
Yeah, the illegal is where you try to drop off in the non-RGBY locations, basically unmarked locations.
This one over here.
Okay, and also the illegal pickup.
Yep, correct.
Illegal pickup, there is no penalty.
Okay.
There is a penalty, right?
Okay, yeah.
Just for pickup 2, there is a -10 penalty.
Okay, so as long as we don't have either of those conditions happen in our 1,000 tests, there's no illegal condition. Okay.
Correct.
So a drop off in a marked location is okay.
Yes.
If it's the wrong marked location.
Yes.
So do you want this to be like 1,000 to be a separate test, or it's the last 1,000 of your training?
I think if you are doing the other evaluation during the training process, then it would make sense just to test that, test this criteria as well. But if you're doing it outside of the training loop, then do it outside.
Okay. So either way is fine, right?
Yeah.
Okay.
And unless unless you have to a lot of random actions is still left over, like if your probability of random actions is still high, if that isn't the case, then it won't really matter whether you are within the training loop or outside the training loop.
I mean, I think it matters for the discounting, right? So in my understanding was that
yes,
in the training loop,
of course you have to track the rewards separately for I mean, the discounted reward is one thing, and then you have to separately track the reward that you're getting over 100 episodes. So the discounted one gets used in your updates and everything, but to decide if the thing that you want to plot and the thing that you want to see between 7.42 and 8.42, that should be your non-discounted reward. And you can keep track of that by just adding up the reward at every step. And then whenever you reach a count of 100, then you just take the average. Is there some confusion with the reward or how?
it was 100 or 1,000.
So 100 is the length of the window, but yes, you have to do it over 1,000 episodes. So obviously the individual reward will vary a lot because that will depend on where the pickup was, where the drop off was. So the idea is that you take average over 100 different steps, 100 different episodes, but then that averaging has to be done over the last 1,000 episodes of your training loop.
So in other words, we go over windows of 100 episodes, and for each of those 100 episodes, we do that figuring out like what the percentiles were. And then we have to do that 10 times in a row. And if in each of those windows of 100, the percentiles are correct, then it's solved.
Yeah, so what this was being discussed the other day as well. So typically what happens is when you have a sliding window, you will just you won't divide it into 100 like 10 non-overlapping sections. You will instead just slide your window. So you'll start at episode 1, and then 1 to 100 you take the average, and then 2 to 101 you take the average. That will give you 900 or so different averages, right? And these values you take their percentile, and those percentiles should meet the criteria.
So you're actually looking for something like 900 sliding windows, and in each sliding window you have that. Okay.
Right. Cool. Again, if there are any questions, please ping me on Slack. I'm still available for some time. And then I'm looking forward to all the submissions by Cement. If you're facing any problem or if there is a delay because you're caught up somewhere, then please do let me know and I'll try to accommodate.
Okay, thanks, Farhan.
Thank you.
everyone.
Good stuff.
Bye.